In this lecture, we will be studying examples of power series. So recall, a power series about x equals a is a series of the following form. So you want to think of it as an infinite degree polynomial in x minus a. The coefficients are these c sub i's. And the central question for power series is, what are the values of x that you can plug in that will give you a convergent series? And recall, we have a test for power series convergence. So when we're given such a power series, we use either the ratio or the root test to find the interval where the series is absolutely convergent. So in this first step, we're looking at the series of the absolute values of these original terms. That gives us an open interval, a plus r to a minus r. So we have an interval centered at a, and we have a minus r as the left endpoint, and a plus r as the right endpoint. And we know within this interval, our series is absolutely convergent. We then have to test the endpoints, because at the endpoints, anything can happen. So at each endpoint, we have to do a manual test, because you can get the series converging absolutely, you can have it converging conditionally, or you can have it diverging at either endpoint. So let's look at some new examples. First, we have the sum n goes from 1 to infinity of n to the n times x to the n. And it always helps to think about series, what we expect them to do before we jump into the computation. And here we note that this is really a competition. N to the n versus x to the n. X to the n, this is a polynomial term in n. And n to the n, you have n in both the base and the exponent. And remember, we looked at this when we looked at our ratio and root tests. N to the n goes to infinity remarkably fast. The issue is that we then have a race where n to the n is going to infinity incredibly fast, and x to the n, if it is going to infinity, we'll get this diverging. But if x to the n is going to 0, you'll have the race of x to the n going to 0 and n to the n going to infinity. The problem is, no matter what x value we put here, n to the n will go to infinity much more quickly than x to the n will go to 0. The result is that n to the n wins dramatically for any x, except the case when x is 0. So we should expect this power series to actually only converge at x equals 0. Well, how do we figure that out? We can use either the ratio test or the root test. And this is a very natural example to use the root test. So recall, for the root test, we set rho to be the limit, as n goes to infinity, of the absolute value of the nth term raised to the 1 over n. Always remember your absolute value signs. In this case, this is the limit, as n goes to infinity, of the absolute value of n to the n times x to the n raised to the 1 over n. We now need to simplify this, and we notice we can distribute the 1 over n amongst two absolute value terms. So we have the absolute value of n to the n raised to the 1 over n times the absolute value of x to the n raised to the 1 over n. We then note n is positive, right? We're looking at the limit as n goes to infinity. So n to the n is positive, which means we can drop the absolute value signs. And the absolute value of x to the n can be rewritten as the absolute value of x raised to the n. And our rules for exponents will multiply. So we have the exponent of the first term, n. We get n times 1 over n, or 1. For the second term, we have the same kind of result. We multiply the exponents. N times 1 over n is 1. So we have the limit as n goes to infinity of n times the absolute value of x. Now we have to note, remember the question here is, what are the fair values of x to plug in? And we note here that if x is 0, this limit will be 0. Specifically, we can say this is equal to the limit as n goes to infinity of n times 0, or 0, but we have to be very specific here. That only works if x equals 0. If x is anything else, think of factoring your x, absolute value of x out. Remember, the absolute value of x has no n term in there. As far as the limit is concerned, it's a constant. So we can factor it out of the limit, and we have the absolute value of x as the limit as n goes to infinity of n. And note, if x is anything but 0, you get some positive constant times this limit, and that limit is infinity. So we get infinity if x is different than 0. So our row from the root test is 0 when x is 0, and it's infinity else. And remember, the key is, for what x do we have row less than 1? Again, note row is always positive because the term inside your limit here is positive. So for what x is row less than 1? Well, let's look at our cases. We said row was equal to 0 or infinity. 0 is certainly less than 1. Infinity is certainly not less than 1. So this is only going to work in this case when x is 0. This means our interval of convergence is the lone point of 0. So the only point at which this series converges is x equal to 0. And this also means our radius of convergence is 0. Remember, the radius of convergence is half of the width of your interval of convergence. Our interval of convergence is just a point. It has width 0. So this is a type of example where your power series only converges at one point. And again, we guessed that because we thought about this. We had this polynomial term versus n to the n. And n to the n is racing to infinity so fast. If x is 0, sure, the terms 0 out. Every term in the series is 0. 0 plus 0 plus 0. But if x is anything other than 0, n to the n is going to infinity so fast, x to the n doesn't stand a chance going to 0 to make the terms go to 0 fast enough to converge. And we confirmed that with this computation. We saw that only at the point 0 does this series converge. Let's look at a second example. And this is an example that we'll actually look at in more depth later on. We have the sum n going from 1 to infinity of minus 1 to the n times x to the 2n minus 1 over 2n minus 1 factorial. And when we see factorials, a very natural test to use is the ratio test. And recall the ratio test defines rho as the limit as n goes to infinity of the absolute value of the n plus first term over the nth term. So let's set this up for this particular example. We have the limit as n goes to infinity of the absolute value. For the numerator, we take every instance of n in our summand and replace it with n plus 1. So we have minus 1 to the n plus 1, x to the 2 times n plus 1, minus 1 over the quantity 2 times quantity n plus 1, minus 1 factorial. And for the denominator, we simply rewrite the nth term. Minus 1 to the n, x to the 2n minus 1, over quantity 2n minus 1 factorial. Absolute value. Again, always remember those absolute value signs. They are critical. Let's clean up algebraically that numerator term. So we have the limit as n goes to infinity of the absolute value. We have minus 1 to the n times minus 1 to the 1. Let's multiply out the exponent here. So we get 2n plus 2 2n plus 2 minus 1, so we have 2n plus 1. And in the denominator, we have the same. We have 2n plus 2 times 1, which is 2, minus 1, or plus 1. And dividing by this term is the same as multiplying by its reciprocal, so we multiply by 2n minus 1 factorial over minus 1 to the n, x to the 2n minus 1, absolute value. And we want to see what we can start canceling. So we see the negative 1 to the n's go. But then we notice we have this 2n plus 1 for this first term and a 2n minus 1 for the second. But we note that we can rewrite things in the following way. This can be written as the limit as n goes to infinity. What we want to do is get some cancellation. We have an x to the 2n plus 1, x to the 2n minus 1. Let's use our rules for exponents to rewrite this as, this is x to the 2n times x to the 1. And then for the second term in the denominator, we have x to the 2n times x to the minus 1. Again, just using our rules for exponents. Then we come to the factorial terms, and recall, with factorials, you can pop off the top terms. The goal is to cancel with this 2n minus 1 factorial. So we note that 2n plus 1 factorial can be written if we pop the first term off. 2n plus 1 times 2n factorial. Okay, we're almost there. We want a 2n minus 1. Well, let's pop off the 2n. And we get 2n plus 1 times 2n times 2n minus 1 factorial. And that is the rewrite that we want. So that denominator will become 2n plus 1 times 2n times 2n minus 1 factorial. And we still have that 2n minus 1 factorial in the numerator. It's a little bit complicated algebraically, but we see we get what we want. X to the 2n's go. 2n minus 1 factorials cancel. What's left? Limit as n goes to infinity of the absolute value. We have a negative 1 times x in the numerator. That's all that survived in the numerator. And in the bottom, we have x to the minus 1. And we have those terms 2n plus 1 and 2n. And now let's see if we can clean this up. Well, this becomes the limit as n goes to infinity. The x to the minus 1 can come up into the top as x to the 1. So in the top, we have minus 1 times x squared. And in the bottom, 2n plus 1 times 2n. Now, we note we can take this. So number one, we're taking an absolute value. X squared is positive. 2n plus 1, 2n is positive. So the negative 1 will become a positive 1 when we take away the absolute value. And we get the limit as n goes to infinity of x squared over 2n plus 1 times 2n. And we can note that as far as the limit is concerned, x is a constant. So we can factor that x squared out. And this is where we get our result. So this will be the limit as n goes to infinity times x squared. So the x squared came out of 1 over 2n plus 1 times 2n. And we note here that this limit is 0. No matter what you plug in for x, you'll either have 0 or a positive constant times a limit of 0. So this is x squared times 0. So this is 0, regardless of the value of x. So it's 0 for all real numbers x. And recall the point of the ratio test is to find for what values of x do we have rho less than 1. Well, we see here rho is 0, no matter what x is. So rho equals 0, which certainly is less than 1 for all x in the reals. Since our rho is 0 for all x, our series converges absolutely for all x in the real numbers. Thus, our interval of convergence is the entire real line. So the interval of convergence is the interval minus infinity to infinity. And our radius of convergence, which is, of course, half of the width of this interval, also has to be infinite. So this gives you another extreme type of example of a power series where it doesn't matter what x you plug in. You will always get a absolutely convergent series. So it converges on the whole real line. It converges everywhere. And so you now see this idea of your interval of convergence In our introductory lecture, we saw one where you had an interval of convergence that had a non-zero but finite radius of convergence. The interval looked like this. In our example 1 here, we saw where this interval collapsed to a point. In example 2, we saw the situation where these endpoints are negative infinity to infinity, and you get the whole real line. So these are the different cases that you can get when you look at the interval of convergence for a power series.